In this video, we'll be taking a look at the 555 timer chip from Texas Instruments. This is arguably one of the most popular chips ever made, and back in the days before Arduino, this was often a centerpiece for electronics kits, largely due to how versatile it is. So in this video, we'll be looking over the 555 chip, how it works, and how you can change the values of the components to change the timing. So here's the 555 chip in one of the most textbook basic layouts you can find, which is called the A-stable multivibrator. That's basically a fancy way of saying that it's able to turn the output on and off all by itself. This layout is also exactly the same as the GamePad's 555 test circuit. So let's go ahead and start up the simulator and we can see how the 555 chip operates. Now right away you can see that the output is turning on and off pretty rhythmically, and it's corresponding with the voltage levels coming in through here, specifically through this capacitor. So this here is the same circuit, but this time I'm going to put it into super slow motion. So let's go turn the simulator on, and we can see two things right away. First is that the output pin is on. It's sending voltage out through this resistor into the LED. At the same time that's happening, current's coming in through this pin, through these two resistors, and it's charging up this capacitor. So if I was to take, for example, a multimeter and probe between the capacitor and ground, we can see that the voltage of that capacitor is slowly rising over time. And if I speed it up a bit more, once the voltage of the capacitor gets up to a certain point, the output is going to switch from on to off. So right now the capacitor has reached the voltage it needs to switch the state of this chip. So you can see that the output is now off, and it's now pulling in current through the discharge line to ground. At the same time, it's also pulling charge out of the capacitor, and it's lowering the voltage again. And once it gets to a low enough voltage level, it switches back to on, the output, and starts charging up the capacitor again. And so this cycle of charging this capacitor and discharging this capacitor is what's actually controlling whether or not the output is on. One better way to visualize how this is working is you can use an oscilloscope. So if I was to use an oscilloscope between the capacitor and ground, you would see a graph like this. So something to note is you can see this line right here. This is the voltage inside of this capacitor at any given point in time. And as the charge in the capacitor rises, once it gets to the very top of this waveform, it's going to turn off the output to the LED. And once it gets to the very bottom, it's going to turn back on the LED. If you want, you can also see these results in real hardware. If you have a 555 circuit or the solder board, you want to use your oscilloscope probe on pin number 6. Once you have that probed, you'll start seeing a graph come in of the capacitor, which looks very similar to the simulator graph. So right now we can tell right away that the amount of time that this LED stays on is directly controlled by this capacitor. So if we make a, for example, smaller value, we can see that there's a much faster rise and fall in the charge of the capacitor, causing the output become even higher in frequency. The same is true in reverse. If we make this a higher value capacitor, it's suddenly going to start taking much longer to charge and discharge it, meaning that the frequency of this flashing light goes way down. But there's other things we can do to change the output of this, apart from just changing the capacitor. We can, for example, change how long the light stays on or turns off based on these resistors here. And the amount of time it stays on and off right now is about the same. So it's on for about the same time that it's off. That's called about a 50% duty cycle. Duty cycle just means how long it is off or on. Let's say I want to make the LED stay on for longer. And if I slow the simulator back down, we can see right here, when this LED is on, charge is coming in and charging this capacitor. So if we want to make this LED stay on longer, we can just increase the amount of resistance in this resistor here. I'll pump the speed back up a bit. And we can see on the oscilloscope graph here, it's taking much longer to charge the capacitor than it does to discharge it. So that means that it's staying on for a lot longer than it's turning off. So there are resources available where you can figure out what components you need to get a certain frequency or duty cycle. There are algorithms you can use to figure out what components you want, what sizes. I frankly would just use a calculator like this one, where you can just put in the times that you want and it'll give you the components you need to reach that time. Now let's take a look at what's inside the 555 chip. The 555 is interesting because it's considered to be a hybrid chip because it uses both analog and digital at the same time. So this right here are the internals of the 555 timer chip, specifically everything inside of this box here. So this chip is a bit complicated, so I'll try and break it down to make it a bit easier to understand. Don't worry if you don't understand it, it's a little bit beyond the scope of this video, but I just want to give you a brief insight into how this works. So to start off with, let me move this box out of the way first, just for a minute. This part right here is considered to be the digital portion of this chip. This is a set reset latch. And what this does is basically it is a 1-bit memory system. So you have here the same circuit as right here. And if I click on set, for example, there's no change because it's already been set. But if I click reset, you'll see the state changes to the opposite. So this turns on and that turns off. And I can do set and reset back and forth, and it outputs and remembers what state it's in. The second part of the circuit is the analog portion, which is all of this right in here. And this is essentially made up of 2 op amps and a rather complex voltage divider. But we can take this, all the principles from it, and break it down into something that's easier to understand. So what I've done is I've taken this circuit, which is just the standard representation of the 555, and changed it into something that's easier to look at. So this right here is essentially the same circuit as this here. So to sort of explain this, I'm going to go back to the original circuit. And right here we have a voltage divider that's generating 2 voltages. In this case, it's generating 6.6 volts and 3.3 volts. And those are the inputs to these op amps. So we have this op amp is looking for a voltage of around 6 volts, and this one's looking for a voltage around 3 volts. So we can remove all of this stuff just for this example and replace it with dedicated voltage sources like this. So we have this op amp looking for 6 volts, this op amp looking for 3 volts. And right here we have the input from the capacitor, and this is the voltage on it, and you can see it's bouncing back and forth between 3 and 6 volts. So what this circuit is doing is that these 2 op amps are tied in directly to the capacitor, and they are measuring the voltage level of this capacitor and comparing it against their own voltage levels here that are generated by this voltage divider. So this one's looking for 6 volts. So as this approaches 6 volts, it's going to get closer and closer to firing this. And as soon as it hits a little over 6 volts, this op amp will fire, changing the state of this latch, which changes the state of this transistor here. We can watch that happen right now. So it reaches 6 volts. And you saw the latch change over. So now the other output is enabled, which is enabling this transistor, which is pulling from the discharge line, which is this over here. So now that this transistor is active, it's pulling charge out of the capacitor through this label here. So you can imagine this is sort of like an imaginary cable linking these 2 together. This is just for the simulator and to make things easier to see. But current's going out of the capacitor through this line into the transistor into ground. It's causing the capacitor to discharge. Now the other op amp is looking at this voltage, seeing if it gets at or below around 3 volts. So if I speed this back up, you'll see the line voltage here. So as soon as it hit 3 volts, it fired the other op amp and switched the states again and turned off this transistor. And that's what it's doing. It's doing that constantly back and forth, where it's just looking to see if it crosses either 6 volts or 3 volts. And depending on which one it crosses, it fires one of these 2 and changes the state. And that's how it's able to oscillate on and off. This sort of setup is kind of similar to a Schmidt trigger, which is a different subject altogether, but it's kind of the same kind of idea that there's 2 different states it's looking to cross before it allows the output to change. So now when we look at the other schematic here, we can see kind of the same deal. It still has the 2 op amps, the latch, and the only thing that's really different is how it's generating those voltage levels. So this right here is its voltage divider, and this one is the high voltage line, so it goes down here. So that's be the 6 volt line. We have here, that would be the 3 volt or low voltage line going to this one. And these wires here go to these inputs on the op amps, so it's both of these are just reading from the same source. For everything else is pretty much the same, and it operates exactly the same. So same deal, it's both of these op amps are looking at the voltage of this capacitor, looking to see which one of these two meets its voltage level, and then fires one of these two respectively and changes the state of this transistor. So exactly the same as what's happening here, it just looks a little bit more complicated. So hopefully you learned a thing or two about how the 555 works. If I lost you during the internals explanation, don't worry about it. It's a fairly complicated chip.